Hi, everyone. Hopefully, your next step of stoichiometry and finding the limiting and excess reactants is going well. I know sometimes it can be a little bit confusing, but that's why I'm here to give you a little bit of a debrief. Really, it's not that much more information to understand. It's just kind of applying what you've learned to understanding if we did chemistry not in a perfect world, but which we're not. We're not in a perfect world, so we have to identify like what is going to run out in an equation known as the limiting reactant and what might be in excess as the excess reactant. And so to show you that, I'm going to work through a problem, and we're going to look at question 2 here. It says if 4.95 grams of ethylene, which is C2H4, are combusted with 3.2 grams of oxygen. Okay, and so we always have to start off with our equations first. And so we have C2H4, and it says it's combusted, which means that it's always added to oxygen and it always produces carbon dioxide and water, are always the products of combustion. And so we start by balancing our chemical equation. That's how we start out every stoichiometry problem ever, because without a balanced chemical equation, you don't have your mole ratios. And so to start, we have 2 carbons on the reactant side, we have 1 on the product. We need to balance that by adding a coefficient of 2 in front of carbon dioxide. And then we have our hydrogens are not balanced. And so, in order to balance that 3 hydrogen with the 2 on the right, the best thing I like to do is actually add a 1.5 in front of there. And I know we can't have a partial coefficient, but what that does is that actually gives us, I'm sorry, I put it on the wrong side. I'm going to add it right here. The 1.5 actually gives us the 3 on of the hydrogens with on the left and the right. But because we know we can't do that, we then need to go back and double everything. And so we have 2 of those, 4 of those, and then we would have 3 of those. And so if we check, our carbons are balanced, our hydrogens are balanced, our oxygens, unfortunately, are not balanced at this time yet. And so we have to keep working with those. And so, in order to balance those, because we have this nice oxygen that's sitting by itself over here, we can really use that to manipulate it. And so we have 4 times 2 is 8 over here, plus 3 is 11. And so same idea, we can use a partial. So what times 2 equals 11? Well, it's 5.5. And so if that balances it, and now I just go through and I double everything, hopefully that will make it nice and balanced. So we have 4 there, 11 there, 8, and 6. And so let's double check our balancing. We have 8 carbons, 8 carbons. We have 4 times 3 is 12 hydrogens, 6 times 2 is 12 hydrogens, and then we have 22 oxygens, where we have 8 times 2 is 16, plus 2 is, or I'm sorry, plus 6 is also 22. So we are now balanced. Each of the coefficients cannot be simplified any further. So we are in our simplest balanced equation here. And so next, what we would do is we would look at what we have for our reactants. And so it's saying we have 4.95 grams of ethylene and 3.25 grams of oxygen. So ultimately, it's asking us which one is the limiting reactant, which one will run out first based off the stoichiometry. So the easiest thing to do with this is to choose one of the products, and let's see if it tells us. It doesn't, or here it says how many grams of CO2 are formed in the second part. So we would just take it out to the product of CO2. But if it doesn't specify a product, you can choose either of the products as long as it remains the same for both limiting reactants. And so ultimately, What I'm going to do is I'm going to take the grams of each reactant in separate equations and take it out to moles of carbon dioxide to see which one produces the least number of moles, because then that tells me that that's going to be the one that runs out first, okay? So I'm going to start off with the 4.95 grams of C2H3. And I know that 1 mole of C2H3 has a mass of 24, because 12 plus 12 is 24, plus 3, so 27 grams. Now I get that from the periodic table, remember, because that's the molar mass. And so grams of C2H3 cancel. I now have moles of C2H3, but I want to get to moles of carbon dioxide. And so I use the mole ratio from the balanced chemical equation to get that. So I know that there's 4 moles of C2H3 for every 8 moles of carbon dioxide. Okay. And so then moles of C2H3 cancel, and I'm left with my moles of CO2. So now I just simply multiply across the top, multiply across the bottom, and take the top divided by the bottom. And so we have 8 times 4.95, and that's 39.6, divided by 27 times 4, 108. So we take 39.6 divided by 108, and we get 0.37, we'll round, 0.37 of a mole of CO2, okay? So now we're going to do the same thing, but now we're going to start with the 3.25 grams of oxygen and take it to carbon dioxide to see which one produces the least. So 3.25 grams of oxygen. We know that 1 mole of oxygen is 32 grams because we take 16 times 2 from the periodic table. Grams cancel. We're now in moles of oxygen. From the balanced chemical equation, we see that there are 11 moles to 8 moles of CO2. So 11 moles of O2 to 8 moles of CO2. And we have our moles of O2 cancel, and we're left with moles of CO2. So the same thing, we multiply across the top, multiply across the bottom, take top divided by bottom. So we take 3.25 times 8, so 26, divided by 32 times 11, 352. So 26 divided by 352 is 0.07. So we can see here that the oxygen is actually producing the least amount of carbon dioxide, so that becomes our limiting reactant, and our ethylene is our excess reactant. Oops, darn touchscreen. And so now it says the second part of the problem would just be figuring out how many grams of this would be formed. So we would always just take it off of the limiting reactant. So since we know we have 0.7 moles, I'm going to add another whiteboard. Oops. Maybe. 0.07 moles of CO2, because we always base it off the limiting reactant because that's the most that it could produce. We would take 0.07 moles of CO2, and you say that 1 mole is 44 grams because 12 plus 32 is 44. And so you take 0.07 times 44. And you get 3.08 grams of CO2 would be formed from this reaction. Okay. And so then you could also figure out like how much would be left over of the excess reactant. Even though the problem didn't ask that, we could still figure that out. And so what we would do in that case, since we know that the oxygen's the limiting reactant, we want to know how much ethylene would be left over. So I would take the 3.25 grams of oxygen and convert it to grams of ethylene to figure out how much would actually react with it. So 32 grams of oxygen gas for 1 mole. And then we have 11 moles of O2 to 4 moles of ethylene. And then 1 mole of ethylene is 27 grams. And so when we multiply across the top, multiply across the bottom, take top divided by bottom, 3.25 times 4 times 27, we have 351 divided by 32 times 11, 352. So 351 divided by 352 is going to be darn close. 0.99. We'll say 1. We'll just basically say 1 if you round it. So it means that that would be 1 gram was used in this production. And so if we had 4.95, so this is used. If we have 4.9 grams that we started with minus 1 gram, we would have 3.95 in excess. 3.95 grams. Okay. So that's how many grams of ethylene would be left over because the oxygen would run out. Okay. So then we have to use this as a opportunity to do percent yield. And so for this, we're going to have to use another problem. So percent yield is basically saying like, okay, so this is how much we expect to get, but we all know that there's also these crazy times that we can lose certain products and reactants through energy release or human error. So how much did we actually get? Okay. And so if we look down at question number 3, it says consider this reaction C6H6 plus bromine gas yields C6H5 Br plus that's bromic acid, hydrobromic acid. And it says, what is the theoretical yield of 42.1 grams of C6H6 reacting with 73 grams of bromine gas? So the first thing you have to do to find the theoretical yield is to find the limiting reactant, okay? So we start with our balanced chemical equations. We have C6H6 plus Br2 yields C6H5Br plus HBr. Excuse me. So for everything that we do, we have to balance this chemical equation. And so our carbons are balanced, our hydrogens are balanced, and our bromines are balanced. So that is really nice. So it's all a 1-to-1 ratio, which makes our life really easy. Okay. And so we know starting with this, we have 42.1 grams of C6H6 and 73 grams of bromine gas. And ultimately, we're trying to figure out the C6H5Br. And so we'll take both of these out to moles of that to calculate what the limiting reactant is. So 42.1 grams of C6H6 is 1 mole. So we would take 12 times 6 plus 6, so 78 total is the mass. And then it's a 1-to-1 ratio, so 1 mole of C6H6 to 1 mole of C6H5Br. And so from there, we would multiply across the top, multiply across the bottom. So it's basically 42.1 divided by 78. Oops. And you get 0.54 moles. 54 moles. Sorry for my, it's very hard to write on this thing. And so then we have our 73 grams of bromine gas. And we know that 1 mole of bromine gas, I don't have bromine memorized off the top of my head. Bromine is 80 if you round it, so it would be 160 for bromine gas because it's Br2. And again, we know that we're in a 1 mole C6H5Br to 1 mole Br2 ratio. And so we would take 73 divided by 160. And it's 0.46, we'll say. Oops, 46, sorry. 46. That looks terrible. Let me rewrite that. 0.46 moles. And so we see here that the bromine gas actually produced the least amount. So you can't always assume that the lower amount is going to be the limiting reactant, because we can see here that the lower amount actually lasted longer. And so bromine is our limiting reactant, where the C6H6 is our excess reactant. Okay. And so now that we know that, we need to figure out what the theoretical yield is. And so based off of this, we would need to convert this 0.46 moles of C6H5Br to grams. And so we know that, I'm just going to erase this. So 0.46 moles. 0.46 moles of the C6H5Br. That is our moles of theoretical yield, but we need to find grams. And so we know that 1 mole of this would be, so we would take 12 times 6 plus 5 plus 80. So that's all of them added together. So 157 grams. And so we take 0.446 times 157. And it's 72.22 grams. So that's what what we would expect theoretically to get produced from this reaction is 72.22 grams of the C6H5Br. But we know that perfect world isn't always going to happen. And so they then tell us what the actual yield was, like in the lab, and it's 63.6. So in order to find percent yield, you always take the actual, which was, 63.6 divided by the theoretical times 100 to get a percentage. And so we take 63.6 divided by 72.22, and we get 88% if we round that, or if we move the decimal over them. 88% yield is pretty high, especially if you were doing this in a high school lab. I would say professionals are shooting for between 80 to 90% yield. In a chem lab like ours, I would expect maybe a 50% yield, to be truthful. So 88% would be pretty high. But that is how you do limiting reactants and percent yields in order to apply this stoichiometry to the real world. Hope this helped. Miss you guys. Take care. Bye.